chemistry time. We haven't done that for a long time. Chemistry 2 time, chemistry time. We're going to talk about reaction rates. Define rate for me in science.
Yeah, the speed at which something
travels. Exactly. This not necessarily the speed at which something travels, but it's we normally think about the rate of something's speed. Here we're talking about reaction rates. We get to describe that in layman's terms as what? We're talking about rate of reaction. What could we call that in layman's terms? That's not really layman's terms. I was going to say how fast the reaction happens. Right? That's what a rate is. How fast something happens. You might at your job have an hourly rate, right? That would be how much money per hour. Rates always have a per. So a rate is some unit divided by a time unit. A rate is always that. You have it for crazy things like how fast you paint your house in square feet per minute or something like that, right? You could have how fast you eat Go-Gurt in tubes per second. Just slow them down, right? I got 20 Go-Gurt tubes per second in here. That would be your rate because it's a per divided by unit of time. How many inches you've grown per year on average throughout your life. All these are rates. So all we're talking about for reaction rates is how fast a reaction proceeds. How fast a reaction proceeds. What would be a useful way for us to measure reaction rates in chemistry?
With a stopwatch?
Yeah, I mean not as a tool, but like as a unit. What units could we use?
Second.
Yep, that would be a good time.
Over time.
Not distance, because they're not usually moving over a distance.
Second.
Time is seconds probably is usually the time.
Yeah.
What would we measure for what would our unit be for the reaction? The how fast the reaction proceeds would be what per second?
For start to
Rate. Oh my goodness, I wrote this down. Hold on.
Molar.
What's going to change about the reaction as it goes?
Changes in molar
concentration. So we're going to have delta concentration of the reactants over delta T. This thing comes up a lot in math. We talk about this a lot in physics, but change in something as it relates to change in something else. There's a special branch of mathematics we use to determine things like this. Do you know what it is? Say it.
Wait, say it again.
There's a special branch of mathematics we use to determine the rate of something compared to the rate of something else. In this case,
calculus.
Yep, the calculus. The calculus is all about, you see this in calculus all the time, dt. We just call it ddt. But this is kind of I wouldn't even be too far to say this is a corruption of this. Delta, as we know in science, means change in. So we're talking about the change in the concentration of the reactant divided by the change in time. It's pretty simple. Something like acceleration is A equals delta V over delta T. A lot of science deals with the change in one thing as it relates to the change in another, and we're going to solve these things algebraically, but the calculus is actually easier. When you talk about calculus in college, when you have that knowledge in your back pocket, doing things like this becomes much easier. The other thing we talk about is that these little brackets and all what we do today and all what you do on your chapter review over the next week or so, these little brackets mean the concentration of that. Well, how do we measure concentration? Usually. What's our unit going to be for this?
L. Moles.
No.
Moles per L.
Well.
M.
Yeah, moles per liter, which is equal to capital M, which we call molar. The molarity. Usually we're measuring the change in concentration, which is molarity. Change in molarity divided by, and for this it's going to be, delta T. What do we measure T in? T is time measured in generally what?
Seconds.
Seconds, yep. So in general, our average rate of the reaction is the change in concentration of the reactants divided by time. Your book talks about collision theory, which is the idea that when a reaction occurs, it occurs because the reactants are bumping into each other and forming a new thing. So for instance, if we have, this would be a very simple reaction, but if we had a molecule of hydrogen, a molecule of oxygen, obviously we're going to have more than that many. There we go. the collision theory is just that when these two things crash into each other, reaction happens, and then what comes out are two water molecules.
Oh. Oh, I see.
Right. Collision theory just says that when these things crash into each other, that the chemical reactions occur when the things that make up the reactants collide. That's all collision theory is. Sometimes there's what we call an activated complex, where it doesn't happen in this case, but for instance, something like, well, I can't even think of an example, so I'm just going to use X. We have thing X and thing Y combine. It forms, for a second, it forms thing XY, kind of like our water, and then that will break down into maybe XY plus Y. This thing here that doesn't stay, well, I almost said alive, but that doesn't exist for very long is called the activated complex. And this is not a great example, but something like this could happen. These things all combine, and then the thing that they make breaks down pretty soon to form two other different things that are kind of like halfway in between. That's called an activated complex. The last thing that the first section talks about is that we last chapter calculated spontaneity, right? We used Gibbs free energy to find whether or not a reaction was spontaneous or not. Spontaneous does not mean fast, and fast does not mean spontaneous. Write that down. A lot of times we hear something like, you might think, oh, I'm so spontaneous, I just went to the lake, and that to you in some way means fast. You know what I mean?
Yeah,
but spontaneous does not mean
happens all of a sudden.
Right. Yeah, and it doesn't mean that it happens all the time. All that spontaneous means is that it's energetically favorable, that that reaction will occur without energy input. That's all it means in chemistry. For instance, the decomposition of diamond into graphite is spontaneous. It's energetically favorable. Diamond has a higher energy than graphite, and so over time, the diamond will convert to graphite. But it takes millions or billions of years for that to happen, if it ever does. And so even though it's spontaneous, it is not fast. And in the same way, things that are non-spontaneous, if you give them enough energy, they can be fast. Let me see the reaction here. The example the book uses is that if you have hydrogen and oxygen floating around together, the reaction where they combine to form water is spontaneous, but there hasn't been enough energy put in there yet for it to actually occur. And it doesn't happen fast. Over time, the hydrogen and oxygen will combine to form water on their own, but if you give them a match and you blow it up, that will happen fast. So even though it's spontaneous doesn't mean it has to be fast, and the obverse is true too. Even though it's fast doesn't mean it is spontaneous. There are three quantities. We could say three intrinsic quantities affect reaction rate. You read what they are. What are they? For a given reaction, three things about it change how fast it can occur.
Temperature?
Yep. Temperature and reaction rate are they proportional or inversely proportional?
Proportional.
They're proportional. So temperature is proportional to rate, meaning that as the temperature increases, the rate increases.
Surface area?
Yep. Surface area, which we abbreviate in math as SA. I don't know. There might be a chemical or science way to abbreviate surface area that I'm not aware of, but I just abbreviate SA. Surface area, proportional or inversely proportional?
Inversely.
Greater surface area?
Yeah, proportional.
Yeah, proportional. Greater surface area. What was an example of this?
Like if you have a rough surface, then the rate's going to be slower.
Nope.
Oh.
If you have a rough surface, the rate will be faster because more of it's exposed. Rough surfaces, higher surface area. The classic example is that like a sugar cube
Dissolves slower than a sugar.
than the same mass of a pile of sugar. Because every one of these grains, you can think of it this way, every one of these grains is presenting all of their sides to the water, which is dissolving them. Whereas in this case, only the outside ones are getting dissolved first. So the classic example is a sugar cube. And the last one?
Concentration.
Yep, so concentration of X is proportional to or inversely proportional to the reaction rate?
Inversely. They're all? Okay.
The concentration of X is proportional to the rate. The higher the concentration, the faster the rate. We have done an experiment before where we take a metal and we pour hydrochloric acid over it and it generates hydrogen gas, and then we tie off the balloon and blow up the hydrogen balloon. You remember that?
Mm-hmm.
One thing that I do to make it go faster is use a higher concentration of hydrochloric acid. So if I use 3 molar versus 6 molar hydrochloric acid, the 6 molar will react faster. All other things being equal. These all imply that everything else is equal. Judging by that, how else could I make the reaction happen faster in that same one? So we're having some metal.
More heat.
Yep, I could do the thing at a high temperature. I could boil the acid first and it would react faster. What else? How could surface area apply? Can I change the surface area of the hydrochloric acid?
No.
Not really, it's a liquid. What could I change the surface area of?
The balloon.
No, that's not reacting. What solid? What solid are we using?
The metal.
The metal. So instead of using a lump of zinc, I could use what?
A big old ball of zinc.
No. What? What would be better than a lump?
Green.
Yeah, powdered zinc. In fact, I don't use powdered zinc. One time I bought magnesium powder to do that, and it was too fast. And not only did it fill up the balloon really fast, which was nice, but it was fast enough that bubbles of acid got in there. And so then the balloon was like half full of hydrogen gas and half full of acid. And so then when I went to pop it, acid got everywhere. No, I didn't actually go that far, but it was a bad reaction. I didn't like that, so we don't use it anymore. I do use the lump. Because in that case, I don't want to have them too fast, because I don't want acid all over the place. Your book goes on to define catalysts and inhibitors. You should know the definition of those. Basically, catalysts make a reaction proceed faster, but they don't get used up. And inhibitors do the opposite. They make a reaction slow down, but they don't get used up themselves. And then it talks about homogeneous and heterogeneous catalysts and inhibitors. All those mean is that homogeneous is in the same state as the reactants, and heterogeneous is in the opposite or a different state as the reactants. Okay, and the last thing we talk about is the math for this chapter, which is what we'll spend most of our time on. You good on these?
I think so.
Are you? Okay. And you're gonna. There was a little bit of math in lesson 1 that we'll work on when you do your chapter review, but it was just that average reaction rate is changing concentration over time, which is pretty easy. That's just a very simple one-step equation. This really is an even simpler equation, but the way we find it is a little bit more complicated. So write this down, please. Rate for a given reaction equals K. What does this mean?
Oh.
The concentration of A.
Concentration of A. So this is concentration of A. Measured how? In what unit?
Molar.
Molar. K is the specific rate constant, which sometimes we're trying to find and sometimes it's just given to you. So sometimes it'll say find the specific rate constant, and then in that case you solve for K.
What is that?
But sometimes it's just given too.
Concentrate.
Specific rate constant, I forget what units. I think it might just be, it's unitless. It's a constant, so it's unitless. Nope, I'm wrong. It's not unitless, but it has weird units. It can be in liters divided by mole seconds. It can be in liters squared per mole squared seconds. It can be just plain seconds. This will have units, but there will be audios. You have to manipulate the rest of it to see what you get. And then rate is, rate, that wasn't very hard. Rate is the reaction rate, and it's measured in what?
Unit per time.
Yeah, but what specific unit per what specific
So
unit?
molars per
Molar per second. Sometimes, and you should know, or you should remember that molar is also moles per liter. So we could call this moles per liter seconds. Oops, moles seconds per liter. Sorry. Wait, is that right? No, I was wrong. It was right. Moles per liter second is right. This is for any one step. If there's other thing you need to worry about, you can do things like this. Rate, sorry, I should start that. Rate equals K. This should be always a lowercase k, forgive me. Times the concentration of A to the m power times the concentration of B to the n power.
This is if there's more than one?
Yep, this is if you're trying to use, if there are more than, a lot of times there will be, even if it's something like even if it's something like two things combining to make a new thing, sometimes only one of the things that's combining, only the concentration of that matters. And if that's the case, we still use the what we call first order rate law. If it's any other order other than first, which means more than one thing makes a difference, we have to use this one. And to find out what these m and the n, for example, if we're trying to find the rate in molar per second, we will be given the constant, we'll be given the concentrations of A and B, but we'll have to find m and n ourselves. And how we do that is we get a set of data, like on page 576, look at page 576, and it has this data. It'll tell us the trials that were done with this. So we have trial 1, 2, and 3. We have initial concentration of A, initial concentration of B, and the initial rate. This one was 0.100 molar. The next one was 0.200 molar.
Do you want us to write that
Yeah,
down?
well, it's in your book. I'm writing it down so that when you watch the video, you don't necessarily have to have your book with you.
Okay.
Okay, what is this for again?
This is how you find m
M?
and n for this equation.
In. Wait, will we need that on the test though?
Yes.
Will you give it to us on
What do you mean? This information here?
Yeah.
No, you'll need this. This is just an example.
Oh, okay.
I'm just writing it down so that you have the information. You just solve the example. Oops. And so all you have to do, m is what we call the order of reactant A. So all this means is that as the concentration of A changes, how does m change? And that determines what we put in here. So for instance, if when we double the concentration of A, if how fast the reaction goes doubles too, then it's first order. Let's write that down. If when the concentration of A is doubled,
If when?
yep, if when the concentration of A is doubled, the rate doubles too, the reaction is said to be first order in A, and m equals 1. Sorry. Am I right? Yeah. Do you see where I got m from? This little m here?
Mm-hmm.
That just means that when we solve it, we will just raise that to the first power, which is just like nothing.
What is that word after first, Mr. Ken?
Order?
Okay.
If when the concentration of A is doubled, the rate doubles too. The reaction is first order in A. Did you do that written down?
Mm-hmm.
I'm gonna do this I'm gonna do a different color above it. So now instead, pretend if when A is doubled again, the rate instead quadruples. What do you think that'll be? Instead of being first order in A, it'll be, guess.
Second.
Yep. So second order in A, and m will equal what?
2.
2. So then we'd raise it to the second power. So look here. What happened when we doubled A? See, the concentration doubled. It went from 0.1 molar to 0.2 molar. So we doubled A. What happened to the rate?
It stayed the same.
Nope.
Oh, it doubled.
It doubled. So what order is it for A?
2.
So since this doubled, I'm going to do this in a different color too. Since this doubled, and it's in column A, and this doubled, that means that m equals what?
2.
No.
4.
Nope. If when the concentration of A is doubled, the rate doubles too, it is first order in A, and m equals 1. So then we put 1 here. Now look at B. In which two trials did we double B?
1 and 2.
Nope. Did we double B?
2 and 3.
2 and 3. So we doubled B. What happened to the rate?
It
Quadrupled. So what is it?
So now it's 2.
So we doubled this, and this is
Quadruple.
times 4. So n equals
2.
So this will be 2. So they'll give you this. They'll give you these two things, and you need to find these from the data, and then you just multiply it all together. So it's like this is 3, which it isn't, and this is 2, and this is 2. We take 3 times 2 to the first power times 2 to the second power, and that would be our rate.
Okay.
Does that make sense? Does that make sense to you, Hedley?
Yes.
Because this is a different kind of math, don't ignore the markers that I threw over. Because this is a different kind of math and a different way of finding it, this a lot of times, like this is not complicated. We're doing things like multiply by 2 like you did in 3rd grade. The math is not hard, but this a lot of times throws people off because it's a weird kind of math.
Yeah.
Mm-hmm.
If you have questions about this, I want you to ask them now, but I will also help you as we do example problems.
I think I just need to do some examples.
You do need some practice.
Yeah.
But furthermore, it's okay not to feel super confident in this right away. You will get it. You just have to be really careful about what the numbers are doing.
Okay.
Does this make sense how you set it up though?
Yeah.
Thanks.
Do you have questions about any of this? So you need to be able to solve what these are called rate law problems. Rate law problems, average reaction rate problems, and then you need to conceptually know the things that affect reaction rates, all the vocabulary, catalysts, inhibitors, that kind of stuff. And then you need to know the meaning of these individual symbols. There's another thing too. Oh, the thing about the activated complexes. Do you have questions about any of this for now?
No.